Welcome to the 7th MATLAB Arduino tutorial. This video will cover how to read and visualize real-time distance data from an ultrasonic rangefinder. The distance measuring sensor we will be using is the Davantech SRF-02, a low-cost single transducer ultrasonic rangefinder. Connect VCC and ground to the plus 5 volts and ground pins of the Arduino, SDA to pin A4, and SCL to pin A5. This ultrasonic sensor communicates with the Arduino over I2C. Distances returned range from 15 centimeters to an impressive 6 meters with 3 to 4 centimeters of resolution. Since it is a single transducer ultrasonic rangefinder, the minimum distance is greater than a dual transducer ultrasonic rangefinder. Reflective objects closer than the minimum distance are in the sensor's dead zone, where measurements returned don't decrease from 15 centimeters. As shown by the beam pattern, the sensor cannot accurately measure the distance to an object that has its reflective surface at a shallow angle so that sound will not be reflected back towards the sensor, or the object is too small to reflect enough sound back to the sensor. Let's look at how to interface this sensor with the Arduino. First, include the I2C library with this line. Initialize the variables mode and distance. The setup serial communication code remains unchanged from the first tutorial, except for the addition of the initialization of the I2C library. In the main loop, we use this code to return distance values when requested by MATLAB. Read the serial data into mode, and implement a switch for case U. GetDistSent is a function that takes the hex address of the sensor and returns the distance reading. Send the distance over the serial port to the computer. After the loop, define the function getDistSent. Cue I2C commands to return the distance in centimeters, then transmit over the bus. After a sensor reading delay, send another command, and request 2 bytes from the sensor. If 2 bytes were returned, read the first byte, and bit shift it 8 bits to the left. Logic OR the previous shifted reading with the next reading to combine the 2 bytes for the final distance value to be returned. Else, return -1 for a failed reading. Last, upload the sketch to the Arduino. After programming the Arduino, let's look at how to read and visualize the real-time data in MATLAB. We'll need the setup serial function created in the first tutorial, the close serial function created in the second tutorial, and a modified version of the readACC function shown here called readDist. The inputs are S, the serial communication structure created by setup serial, and mode, a variable that matches the character of the appropriate case in the Arduino switch statement. Send the character in mode to the serial port, then read the value returned in the correct format. Here's an overview of how to make 3D graphics visualizations in MATLAB using hgtransforms. First, create an axis and adjust the view for 3D. Second, create surface objects to form different shapes. Third, create the hgtransform graphics object by combining or parenting the surface objects. Fourth, draw the objects in the axes. And fifth, manipulate the position, rotation, and scaling of the graphics object using sensor data. Put this all together in the animation3d.m script to read distance data and animate a visualization. In the first cell, enter the COM port that the Arduino is mounted to, and subsequently run setup serial. The third cell creates a figure, adds start-stop plotting buttons, a close serial button, and a slider for modifying a filter parameter. Next, the fourth cell creates the graphics object used in the visualization. Create an axis and adjust the view using these functions, setting axis limits and preventing auto-scaling. Use the cylinder and sphere functions to generate X, Y, and Z matrices for the respective shapes. Then plot different orientations of these 3D shapes and assign all surface object handles to the vector S. Last, create an hgtransform object with the parent property containing the axes handle created above, and set the parent property of the surface objects to the combined hgtransform object. The term parent property is a relationship between objects, allowing the surface objects we created to be grouped together so that hgtransform operations can be performed on the combined object. Finally, in the last cell we will animate the graphics object with real-time sensor data. Since we are using the ultrasonic distance sensor, set the variable mode to equal the character U. Create a while loop to repeatedly get distance readings until the stop button is pressed and changes the user data property. A low-pass filter discussed in Tutorial 4 may be applied to smooth the raw data. The make-hgtransform function creates transformation matrices for translation, scaling, and rotation of graphics objects. Here, I translate about the y-axis and proportionally scale using distance measurements. Manipulate the hgtransform combined object by setting the matrix property with the product of the translation and scaling transformation matrices. Running the script, here's the output. As I move the reflective object closer to the distance sensor, the graphics object gets larger and moves closer to the y-axis. As I move the reflective object away from the sensor, the graphic object reduces size and moves away from the y-axis. Adding filtering greatly minimizes the noise, and the graphics object appears stationary when the reflective object is a constant distance from the sensor. Decreasing the filter coefficient even further results in much more smooth movement. Reducing the filter coefficient even further results in much more fluid movements, though with additional lag. The effective translation can easily be seen from the side view. Looking at the graphics object head-on shows the effects of scaling. Here you can see the dead zone of the sensor. Though the reflective surface's distance to the ultrasonic sensor is less than the minimum range, the sensor readings don't decrease. Thank you for watching. Please visit matlabarduino.org for more videos.